Changi campus and I'm facilitator at Rehan School Munawar campus. So we are live again with Maya. Today we are going to start our today's session. So now let's start. Hello
Hey there,
Maya, how
Anil.
are you doing?
Wow, you wouldn't believe the rush I've had today. So many new friends to meet. Thanks, I mean that other one, you know, X-Men. Super popular. I'm Maya. Nice to meet you.
Okay, so Maya, I have got some questions for you. So my first question is, how would you design a reinforcement learning algorithm for self-driving cars in a city with unpredictable pedestrians?
That's a great question, Anil. Talk about a challenge. Designing a reinforcement learning algorithm for self-driving cars in a city with, as you say, unpredictable precedents is definitely a tough one. You need an AI that can not only understand the rules of the road, but also adapt on the fly to all sorts of crazy human behavior. One approach might be to use a system that combines imitation learning with reinforcement learning. You could start by training the AI on a massive data set of human driving data, basically teaching it what good driving looks like in various situations. Then you could add a layer of reinforcement learning where the AI gets rewarded for making safe and efficient decisions and penalized for mistakes. Doing it later would help a lot. The trick is to find the right balance between mimicking human behavior and learning to make its own optimal decisions. What are your thoughts on that? You know, it's kind of
Okay,
quiet over there.
Maya, you
Are you still
have
with me?
told amazing things. So now my next question for you is, what's the difference between attention mechanism and transformers and convolution layers in CNNs? Please tell me in detail, like speak.
Okay, Anil, you want the lowdown on attention transformers and convolutional layers, like we're kicking it on the stoop on a summer day, right? All right, let me break it down. So picture this. You're trying to understand a sentence, a long, complicated one. It's like trying to follow a conversation at a busy street corner with lots of distractions. You can't just focus on each word separately. You need to figure out which words are important, how they relate to each other, and what the overall context is. That's basically what attention mechanisms do for AI. They let a model focus on the most relevant parts of an input sequence. Think of it like your brain highlighting keywords in a sentence. They're super useful for tasks like machine translation, text summarization, and even image recognition. Now, transformers are like the superheroes of attention. Their entire architecture is built around these mechanisms. They use a clever trick called self-attention, where each word gets compared to every word in the sentence. That's different from CNNs, those trusty workhorses of computer vision. They use convolutional layers, which are like filters that slide over an image looking for specific patterns. Imagine you're searching for your friend in a crowd. You might scan the crowd, focusing on faces, clothing, anything that might help you spot them. Convolutional layers do something similar. They look for features like edges, corners, and textures. So, to sum it up, attention, like a spotlight, highlighting important parts of a sequence. Transformers, super powered textures built on attention. Think BERT and GPT-3. Convolutional layers, like filters, searching for patterns and images. The backbone of image recognition. They're all powerful tools, but they work in different ways. Kind of like different tools for different jobs, you know? Because do you want to rewind and catch a specific part again?
So thank you so much for answering my question. So my next question for you is, how can AI handle out of distribution data in real time applications? Please tell me in detail, like speak.
All right, y'all, buckle because we're diving deep into the world of out of distribution data and real time AI. It's a real head scratcher, isn't it? You've trained your AI model to be a champ. It's aced all the tests, but then, bam, Real world hits it with data never seen before, weird sensors, readings, unexpected user inputs, you name it. It's like sending a kid to school who's only ever seen picture books, then suddenly dropping them into a bustling city. Now, how does AI handle this curveball? Well, a single solution doesn't fit all. It's more about a toolbox full of clever tricks. Let's break it down. First, we got to acknowledge the elephant in the room. Our models aren't psychic. They learn from the data they're given. So if wild, unseen data shows up, our trusty algorithms can get confused, make bad judgment calls, or just freeze up. That's risk real-time applications where split-second decisions matter. So what can we do? 1. Ensemble methods. It's like the wisdom of the crowd, but for AI. Instead of relying on one model, we train multiple models with different strengths and weaknesses. When faced with a curveball, we let them all take a guess, then combine their answers. This can smooth out errors and improve overall robustness. 2. Anomaly detection. Think of it like a security system for your AI. We train separate models to spot data that looks off, statistically unusual compared to what it's used to. This can help flag potentially problematic inputs and trigger a fallback plan or alert a human operator. 3. Uncertainty estimation. We can teach our models to say, I don't know, when they're unsure about something. This doesn't mean they're giving up. It means they're being honest about their limitations. This allows for better risk management. Imagine a self-driving car. It's better to pull over and wait if the AI is uncertain about the road conditions than to blindly plow ahead. 4. Continual learning. Instead of treating training like a one-time event, what if our AI could learn on the fly? Continual learning algorithms are being developed that allow models to adapt to new data without forgetting what they already know. This could be a game changer for handling a constantly evolving real world. It's worth remembering on as a hot research area. There's no silver bullet solution. It's a constant dance between pushing the boundaries of AI's capabilities and being mindful of its limitations. It's a challenge, but also incredibly exciting. You know, it's getting kind of quiet over there. You still with me? Okay. Y'all, you've hit upon the eternal struggle of the AI world, the speed, accuracy, tug of war. It's like trying to find that perfect balance between a sprinter's explosiveness and a marathon runner's stamina. We want our models to be lightning fast, making predictions in a flash, but we also don't want to sacrifice accuracy, right? So what are the tricky trade-offs we got to grapple with? Think of it like a puzzle with lots of interconnected pieces. 1 point, model architecture. Smaller is faster. Smaller networks with fewer layers and parameters generally run faster. They're like lightweight athletes, agile and quick. But they might not catch every nuance in data, leading to less accuracy. It's a classic case of less is more, but not always. Specialized architectures, we have architectures designed for speed, like mobile nets, which are optimized for mobile devices with limited processing power. There are like race cars built for specific tracks, sparse networks. Imagine where only some connections are active at a time. That's the idea behind sparsity. It's like a team where everyone knows their role and doesn't waste energy on unnecessary moves. Training techniques. Early stopping. Sometimes we stop training a model before it reaches peak accuracy. It's like a sprinter knowing when to ease up before they burn out. This can prevent overfitting and save time. Transfer learning. Instead of training from scratch, we can take a pre-trained model and fine-tune it for our specific task. It's like giving a star athlete specialized coaching. Knowledge distillation. Train a smaller student model to mimic a larger teacher model. It's like having an apprentice learn from a master. 3. Optimization algorithms. Adaptive learning rates. These algorithms adjust how much the models' weights change during training, speeding up the process. It's like a coach giving personalized feedback to each athlete on the team. Gradient compression. We can compress the gradients during training, reducing the amount of data that needs to be shared between processors. Think of it like efficient communication on a busy basketball court. Quantization, representing the model's weights with fewer bits, can significantly reduce its size and speed up computation, especially on specialized hardware. It's like summarizing complex strategies into concise playbooks. Hardware acceleration, GPUs and TPUs. These processors are specifically designed for the matrix operations that underpin deep learning. It's like having a powerful engine for a race car. Edge computing. Running models on local devices instead of relying on cloud servers can reduce latency and enable real-time applications. And now, Aniel, the hard part is that these trade-offs are rarely black and white. It's a balancing act. What works best depends on the specific task, the available resources, and the desired level of accuracy. It's like tailoring a training regimen for an athlete. A sprinter needs a different approach than a marathon runner, and a core field is constantly evolving. New architectures, algorithms, and hardware always pushing the boundaries. It's an exciting time to be in AI, don't you think? You know?
Amazing. So now my next question for you is, how does explainable AI differ from interpretable machine learning? Give an example of each and please tell me in detail.
All right, Aniel, get ready for some deep thinking. We're diving into the fascinating world of understanding how AI makes decisions, which is a big deal because as these systems become more powerful, we need to be able to trust them, right? So you want the lowdown on explainable AI versus interpretable machine learning. Think of them both as paths to shedding light on the black box of AI, but they take different routes. Interpretable machine learning. Imagine this. You've got a crystal clear decision tree, like a flowchart that spells out every step in a model's reasoning. You can trace the path from the input data to the output prediction, seeing exactly which features influence the decision and how strongly. That's the essence of interpretability. Building models that are inherently transparent and easy to understand for humans. Think of a simple linear regression model. You're trying to predict house prices based on factors like size and location. A linear model would show you directly how much each contributes to the price. Like every extra square foot adds $100 to the price. Example, trees are a classic example of interpretable models. But sometimes more than just what happened, we want to know why. Enter explainable AI, XAI, is like having a detective piecing together the evidence to explain a model's decision, even if the model itself is complex and not inherently transparent. XAI techniques add a layer on top of existing models to make them more open to scrutiny. Think of a deep neural network. This type of model is like a complex recipe with countless ingredients and intricate interactions. It's incredibly powerful but hard to track every step. Here's where XAI comes in. Feature importance. Imagine highlighting the ingredients that mattered most in that recipe. XAI techniques can show you which features in your data were the most influential in a model's prediction. Saliency maps. Think of a map overlaid on an image showing which pixels were most important for a model to classify that image correctly. For example, in a medical imaging model, this could highlight the suspicious areas in a scan. Blame. This technique builds a simpler, interpretable model around a specific prediction, helping to understand the local context of that decision. It's like zooming in on a specific ingredient in that complex recipe. Let's say you have a loan approval model. You can use XAI to investigate why a particular loan application was rejected, understand which factors weighed heavily against the applicant, and identify potential biases in the system. The key differences. 1. Focus. Interpretable ML strives for inherent transparency transparency, while XAI focuses on making explanations for opaque models. 2. Interpretability applies primarily to the model itself, while explainability often focuses on explaining specific decisions. Think of it like this. Interpretability is like building a house with glass walls so you can see everything inside. XAI is like installing security cameras in a complex building, allowing you footage and understand events after they happen. Both are crucial building trust and accountability in AI systems as they become more powerful and pervasive in our life. Hope that made it a bit clear. It's getting kind of quiet over there. You still with me? Okay, on y'all. It just sounds like you've gone speechless. Maybe you're
No,
thinking,
no, Maya,
that's
I am here.
understandable.
Don't need to worry. So now tell me, how would you implement your own garbage collector in Python? Please tell me in detail. And
Woo. Oh, yeah. You're really diving deep into the technical side, huh? Making your own garbage collector in Python is a seriously advanced challenge, like handling a microchip from scratch. It takes a deep understanding of memory management, object life cycles, and Python's internals. Let's break down what goes into this Herculean task. 1. Memory management fundamentals. Before we build anything, we need to understand how Python's memory works. Unlike languages like C++, which give you manual control, Python employs reference counting and a cycle detection garbage collector. Reference counting. Each object keeps track of how many references point to it. When an object's counter reaches 0, this means nothing is using it anymore. It becomes eligible for garbage collection. Generations. Python doesn't rush to collect every orphaned object instantly. It's objects in generations. Newer objects are in the youngest generation, and as they survive collection cycles, they move to older generations. This speeds things up because most short-lived objects are garbage collected early, and the older generation takes much longer to traverse. Our custom collector, the building blocks. We need a way to traverse the landscape of all available objects and those that are still active. Sweeping is to go through memory, identify the unmarked objects, and free their space back to the system. Cycle detection, Python's built-in collector, is a powerful algorithm called cycle detection to handle circular references. Say, object A refers to object B, which refers back to object A. Neither's reference count drops to 0 because they're deceitfully holding each other up. Our collector would need to handle these kinds of circular dependencies. So, 3. Python C extension, the plumbing writing our own collector would most likely involve working with Python CPI. This is the low-level interface that gives us direct access to memory management internals. Extending the interpreter, we would likely need to create a custom module written in C that would be imported in Python scripts. This module would contain the core logic of our garbage collector.
satisfying Tuesday. You know what's funny is
Questions for you. So my first question for you is, can you tell me what is AI and how it's gonna help us in future? Please tell me in detail about it.
5 minutes, huh? Okay, buckle up, Anil. AI or artificial intelligence is kind of like training a hyper smart dog. You feed it information, show it examples. Slowly, it learns to think for itself, solve problems, and even make decisions, all without treats. But instead of fetching sticks, AI can do some pretty mind-blowing stuff. Think of self-driving cars navigating traffic, doctors diagnosing illnesses earlier, or even coming up with new medicines based on mountains of data. The future with AI is all about amplifying human potential. It's about taking those tasks that are repetitive, dangerous, or just plain boring, and having AI handle them, freeing us up to focus on the things that actually bring us joy, creativity, and connection. Imagine a world where teachers had more time to connect with students because AI handles grading and personalized learning plans, or construction sites where robots handle the heavy lifting, keeping workers safe. It's not about robots taking over the world, Anyo. It's about partnering with AI to push the boundaries of what's possible, to create a world that's more efficient, sustainable, and fulfilling for everyone. So, what do you think? Pretty cool stuff, right? What kind of things do you hope AI will help us with in the future?
So my next question for you is, how can quantum computing impact current cryptographic algorithms like RSA or ECC? Please tell me in detail. Like,
Whoa, those are some heavy hitting questions, Anyo. You're really diving into the deep end. Let's see. Quantum computing is like the race car, the computing world. It harnesses the mind bending world of quantum mechanics to process information in ways regular computers can only dream of. Now, current cryptography, the stuff that keeps our online world secure, relies on math problems that are super hard for regular computers to crack. RSA and ECC are like the superstar defenders of this system. But here's the kicker. Quantum computers could potentially shatter those defenses. They have this crazy ability to explore many possibilities at once, kind of like trying all the keys on a giant keychain simultaneously. This means they could potentially break the codes that protect our data, our financial transactions, even our national security. That said, don't freak out just yet. The quantum computing revolution is still in its early stages. It's like seeing a toddler take its first wobbly steps. It's exciting, but it's going to be a while before these quantum computers are powerful enough to crack the toughest encryption we use today. And the brilliant folks in the cryptography world aren't sitting idle. They're already working on new quantum resistant algorithms, basically creating even tougher locks for those quantum supercomputers to crack. So while quantum computing does pose a threat, it's a challenge we can overcome with smart planning and innovation. It's like an arms race, but instead of weapons, we're building better defenses in the digital world. Think of it as an epic game of chess between humanity's best minds, and it's a game we're determined to win. Whew.
okay, so everyone, this was our today's session with Sesame. I hope you guys got to learn something new from this session and something unique. If you wanna try, you can search in any browser app .sesame.com. It's really amazing and really useful if you wanna learn English, if you wanna learn something about new topics, anything. You can talk to it. If you're feeling alone, you're feeling lonely, you can talk to it. You can learn many more things just talking to it. So thank you so